Okay, so let's continue from where we left off. So we ended at current. We got to know what current is, and we said that current is a secondary effect to the flow of energy, right? In other words, it is just that it's equal to, or it's just like saying that the way we see energy flow through a circuit is by the fact that electrons move as current. Is that okay? Great. Now, technically, or in a realistic view, the electrons actually move from the negative to the positive. Okay, I need you to understand this one. Electrons move from negative terminal to the positive terminal. However, for the sake of history, you see, when they discovered these things, well, at the time where they were building on these things, they had the mentality that we had some form of positive charges that flow from the positive terminal to the negative terminal, right? And over the years, that's what they used and said, right? So, I mean, technically, it doesn't change anything by trying to correct the fact that electrons are rather moving. So, we rather decided to go with it and call that conventional current. Is that okay? So, when we talk of current, yes, we know that it is electrons moving to positive charge, but we still take it as positive charges moving from the positive to the negative. Is that okay? We call this the conventional current. And recall that when we talk of positive charges, we are talking about what? The absence of electrons. Is that okay? And it actually makes sense in a way because anytime an electron moves, it leaves a hole, right? So if an electron is moving in one direction, that means it will be creating holes or absence, it will be creating, yes, absence of electrons in the opposite direction. So technically it makes sense and actually doesn't change anything. Okay, so conventionally we take current to be positive charges moving from for the anode to the cathode. So take note when we are talking about electron current and conventional current. Now, current is measured in units of ampere or amps for short. So if you hear something like 1 amp, 15 amps, 0.5 amps, okay, that is a measurement for current. Is that okay? All right. Now, take note that the electrons have energy. Okay, so Samuel, Emmanuel, you asked the question. So the electrons do have energy, and they also get accelerated by the field. Is that okay? Now, from concept of mechanical work, an external force must act on a load to move it. I think I already mentioned these things, right? So like I said, you cannot pull yourself up. So the electron cannot move itself. Something has to move the electron. Is that okay? So this means that the electron cannot move itself for work to be done. So where does the external force come from? Okay, so I asked this question twice. It comes from the ion cores. Remember, we have specific ions or charges that are sustaining our electric field. Those are the charges are due to the ion cores at the anode and the cathode. Is that okay? So this generates the force that moves the electrons. So the electrons gain kinetic energy as a result of the action of the field, but the energy is not what is powering the load. Okay, so those who are confused, in fact, I made this note as if I was talking, right? So I'll share it with you, go over it, read, you would understand. It's basically like me talking to you. Okay, that's how I prepared the notes. Okay, now, so to add more to what we're talking about, okay, the energy that we are talking about that is powering the system, first of all, floats closer to the speed of light. Okay, now why am I saying close to the speed of light? This is because the material medium in which it flows affects the speed. Is that okay? So close to the speed of light. Now there is something called electron mobility. Electron mobility. It is a measure of how quickly electrons can move through a particular material when an electric field is applied. Okay, a measure of the speed or how quickly an electron can move through a material when a material when an electric field is applied. Now this thing that we call electromobility is actually an intrinsic property of materials. So it means that if I pick something like copper, right, it has a certain mobility which actually would depend on the field, I think, because electric mobility depends on the field, and it is measured in units of square centimeters per volt second or meter squared per volt second. Okay, take note, these things, most of the times you don't have to worry about this. We are just learning about these things for understanding of what is to come. Is that okay? Good. So we can say that no, we can say mobility is actually related to the speed of electrons in the material. Okay, so there is a relation that's oh, I made a mistake. So you can see here that electrons do not flow at the speed of light. Okay, electrons do. This is something that I need you guys to really understand. Electrons don't flow at the speed of light. Okay, the speed of electrons is nothing comparable to the speed of light. All right, so we have something also called drift velocity. Now drift velocity is the net average velocity of charge carriers such as electrons in a particular direction under the influence of a field. So this means that when we apply an electric field, that is when we connect a circuit to a power source, the electrons tend to move, and the speed at which they move, remember we said that the electrons don't just move by on their own accord, they are drifted by the field, right? So the speed at which they drift is what we call the drift velocity. Is that okay? And it is definitely it is always due to the influence of the electric field. Is that okay? Good. Now drift velocity is a component of the overall motion of the electrons in the conductor. Okay, so we are not talking about a single electron's movement, we are talking about the entire thing called current. So you can take as the speed of the current, right? That's what drift velocity is talking about. Okay, so it is the velocity that contributes to electric current. Remember we said current is a measure of charges that are moving in a particular direction per cross-sectional area, so across a given cross-sectional area per unit time. Okay, so this happens because the velocity actually has an influence over that, and there is actually a relationship, right, between electromobility and electric field and drift velocity. This is it. So the drift velocity, that is the speed at which the current will move or the electrons will drift, depends on the electric field. Now this value here, the mu, is what we call permittivity of free space. Okay, it's a constant as many people will say, that is supposed to make sure the unit comes out right, but there is something called permittivity of free space. You can read about it if you are interested. Okay, all right. This is interesting. Okay, so still on our thought experiments and studies, right? The drift velocity of electrons in a typical electrical conductor is relatively low. Okay? Now, relatively low, what values are we talking about here? We are talking about a few millimeters per second. Okay? So if you compare it to the energy which is actually moving closer to the speed of light, and the speed of light is 300 million meters per second. I mean, how can you say that something that is moving at a speed of a few millimeters per second releases something that's, or transports something that is moving at 300 million meters per second? That's not possible. Is that okay? That is not possible, and that is something that I need you guys to understand. Okay, I need you guys to understand. Okay, so the actual value can vary depending on factors such as the electric field that has been applied, the material properties, and the charge carrier density. Okay, now, like I said, these are not things that you should really worry your head about, but you need to know. I need to mention them so that I can refer you, okay, when I need it to. So moving charges, as we saw already, create the magnetic field, okay. The magnetic field together with the electric field is what transmits the energy. Please take note of this point. The magnetic field together with the electric field, okay, is what transmits the energy that makes the device work. Now, Veritasium, which is a popular YouTuber, I think I'll post his. He did a very interesting thing on this thing I'm talking about. He did a very interesting experiment, and it attracted a whole lot of internet ridicule. But he was right in the first place. Okay, so I'll share the videos with you on the WhatsApp platform so that you can look at how the animations and everything will make sense to you. Okay, but in the beginning, yes, it will be counterintuitive because that is not what you've been made to know. Okay, so don't worry, just be open-minded and you'll be fine. Okay, so the energy that powers the device in circuit travels close to the speed of light. I think I've been even mentioning these things over and over and over. Okay, this could not possibly be carried by the electrons with such low speed. Okay, and I mean, we are talking about 300 million meters per second against a few millimeters per second. That is not physically even possible, right? So yes, please. What I need you to take from this point is that the energy that powers our devices is not the same energy that is carried by the electrons. Okay? All right. Great, 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 great. So, like I said initially, this kind of challenges and that we are facing right now is because when circuit limit was postulated, right, or proposed, circuit theory was proposed, certain assumptions were made. Is that okay? Certain assumptions were made. And you and I know that if an assumption is made and that assumption breaks down, then the theory also breaks down. Is that okay? So I'm going to touch on a few assumptions that were made in circuit theory, okay? But unfortunately, I don't see books talking about these assumptions. They just start and they are talking about what circuit theory is about, forgetting to mention the assumptions, because so far as the assumption holds, circuit theory will hold. But the moment the assumption breaks down, circuit theory breaks down, okay? And in current or modern electronics, trust me, circuit theory has already hit its limits. Okay, now why am I saying that? Now, in modern electronics, we often see very high speed signals. Okay, and these are usually due to what we call fast rise times in ICs. I know this will not be very familiar to most of you. Okay, but just keep this note, read it when you get it. Okay, now circuit theory is a fundamental concept in electronics. Okay, it encounters limitations. Listen to this carefully. Circuit theory encounters limitations when we are dealing with magnetics and electromagnetic fields, especially at these high frequencies. Okay, now while circuit theory may reach its limits in systems with high frequency and frequency component, it remains applicable, effective for low frequency DC applications. Okay, now I have notes on the statement of the circuit theory assumptions. I'll show them to you. Okay, now in these cases, careful application of circuit theory can yield accurate results without significant challenges. Okay, so yeah, though circuit theory has hit its limit, it doesn't mean that every circuit that you design as circuit theory is not applicable. We are looking at situations where we are dealing with very fast circuits, high speed circuits, right, or high speed designs. That's when circuit theory actually becomes challenging. But for normal DC low frequency stuff, you can still manipulate your way around using circuit theory. Okay, so dealing with electromagnetic fields requires a solid foundation in electrodynamics and some quantum mechanics, which can be challenging for many practitioners. The treatment of this field in electronics involve complex understandings of the interaction between electric and magnetic field. Is that okay? So basically, this is just to explain some of the things. Now, what are some of the assumptions that were made for circuit theory? The first one, I'm going to read out just a few of them, right? Says that circuit theory assumes that the circuit is in a steady state, meaning that voltages and current have reached constant values over time. Transient and time-varying behavior are often neglected. And you can't do this in modern, you can't say this doesn't hold in modern design, because ICs have these transients every time they switch. Okay, because they are switching at very high speed, and this introduces changes in electromagnetism, which we know would, according to Faraday's principle, a change in electric field induces a change in magnetic field, and vice versa. Okay, so circuit theory doesn't really work when we are dealing with fast rise times. Okay, it also assumes the behavior. Circuit theory also assumes that the behavior of circuit elements is linear. Is that okay? So here we are talking about things like resistors, capacitors, inductors. Is that okay? So yeah, and it goes on, goes on. In fact, now look at this one. It says no electromagnetic radiation. That means that when we are using circuit theory, you don't consider any sort of electromagnetic radiation. But these are things that are happening, okay? In circuit design, we call some things crosstalks, interferences. Led to circuit theory alone, these things won't happen, because these things are all electromagnetic phenomena. Is that okay? So circuit theory has its place, but not in modern electronics, because right now the speeds that we are dealing with is crazy. Okay, and according to circuit theory, signals propagate instantaneously. So it's like the moment I switch on the circuit, there's energy is everywhere, but that's not the case. Okay, it takes a considerable amount of time for the energy to propagate. Is that okay? But it all depends on who is looking. Okay? It all depends on who is looking. Now, assuming you are running with an ant. Okay? Let's just assume that you are running with an ant. How do you think the ant will see you? The ant will probably see you as flash, right? Because just one stride, all right? Just when you take one step and you are like a whole lot of centimeters away from the ant. So the ant will think that, oh, wow, this person is the flash, right? But if you are running with a cheetah, the cheetah won't see you like that. So if you are running with the cheetah will see you to be slow. Is that okay? So it's a matter of what? Perspective. Is that okay? It's a matter of perspective. When it comes to high-speed design, it takes time for energy to propagate. Energy doesn't appear instantaneously, as circuit theory assumes. Okay. So once all these assumptions are failing, circuit theory does not hold in those kind of systems. Okay, so let us understand these things. Okay, signal takes time to propagate. There is electromagnetic radiations in circuitries. Okay, all right. So I have other stuff here that you can read about if you are interested. Okay, all right. So any questions up to this point?